is Professor Avi Wigderson from the Institute for Advanced Study, one of the greatest mathematicians and computer scientists of all time. Winner of the Nevanlina Prize, the computer science analog of the Fields Medal, plenary lecturer at the ICM in Madrid, winner of an expository prize for the masterpiece on expanders, who will speak on some trivial Euclidean geometry today.
Thank you. Do I deduct it from the time you were? Okay, so thanks, Doron. Doron is absolutely right. I'm going to tell you about just a very, very simple problem that even the two-dimensional board suffices to describe. It's a problem about points and lines. This joint work with Boaz Barak, Zeev, Dvir, and Amir Yehudayoff. So let me recall for you the what's called the Sylvester-Gallai theorem. Actually, it's not exactly, it's really, the theorem is by Gallai and by Melchior. These guys are those who made the theorem. Sylvester conjectured it, and also Erdős conjectured it. And because of Erdős conjecture, Gallai solved it, and because I think Sylvester's conjecture, Melchior solved it. But this was a conjecture. And these are the guys that are responsible for the theorem. And this theorem says the following. Suppose you have n points in the, let's say in the plane. It can be in any dimension in the Euclidean space, but let's say in the plane. And suppose that you know, so here are the points. Suppose you know that whenever you take 2 points and pass the line through them, you meet a third point in the set. So let's call this set P. Suppose, so for every pair of points, when you pass the line through them, you meet a third point. Okay, for every point. So we call a line like this. So let's say for 2 points in our set, let's say P and Q. So this will be the line through the points P and Q. And suppose that for all P and Q, L of PQ intersects non-trivially P minus Q. This is non-empty. Okay, so if we call such a line, so call such a line special. So this kind of line is a special line. Why special? Because typical lines through generic pairs of points don't have this property. So we are looking at the situation that every pair of points is special. Every line through every pair of points, if this is a line, there has to be a point somewhere here. Okay, so the question is, how do configurations in which every line is special look like? Can anybody give me an example?
They're all on a line.
Yeah, they're all on a line. I'll pay you later. This is such a situation. Every line here is special. Now, another example, different example. There you go. Okay. So what the theorem states is that this condition that every line is special implies that it is configuration. There is no other way. That's a theorem. Actually, it's not, it has several really slick proofs, but obviously people like Sylvester and like Erdős didn't see them, so it's somehow. You want to see a proof? How many people have not seen this? Okay.
Yes,
So it's a
I
non-trivial.
talked about it last year.
Yeah, every-
But I wasn't there.
last year, Doron, you don't have high expectations. So you have, suppose you have such a configuration, so you have all this, and suppose they are not, so assume not. Well, if they are not, then there is some point that is not on some line, right? So now you can start talking about the distance between lines and points that are not on them. Okay? And let's find the minimum such distance. So let's find a line, L, and a point P, which P is not on L, such that this distance is minimal. Okay? Between any point and any line in this. Okay, so and now we prove a contradiction. How do we prove a contradiction? We found the minimal distance, and now let's show that there is an even shorter distance between some point and some line. But how do we know this? Well, this line is like all lines in the configuration. This may not be a point in the configuration, but there must be some 2 points here. But in fact, in every line, there are at least 3 points. So 2 of them will be to one side of this intersection, right? Okay, then I claim that the distance from this point to this line is short. That's all. Okay. I'm going to give only sketchy proofs here because of my severe time limit. So what is the situation we are interested in? We are interested in generalizing this theorem to the approximate version. So what would be an approximate version? You can think of several, but here's the situation that we are interested in. So what is sort of approximate Sylvester-Gallai configuration, what we are going to say, so beforehand, let me recast the Sylvester-Gallai theorem in the following way. So what is one Sylvester-Gallai configuration? Is that for every point in our set, if we look at every point, all lines through P, also special lines. So let me write it here. Special lines through P contain all points, all of them. Right? That's the same as saying that every line is special. And what will be delta for any positive delta? Is to say that for every point, special lines through P contain not all the points, but maybe a delta fraction of them, L times points. Okay? So these are now very swastic, since you are so good to give us more than one example. Give me an example of a 110 configuration, where not all points are on one line.
10 lines.
10 lines. How many points should I put on it?
110.
110. That's good because it's simple. So if I take 10 lines, and in each of them I put n over 10 points, then it will satisfy this condition, right? So definitely not all of them are on one line. And you can see that these 10 lines, you can take them not only in the plane, you can put them in space. So if you think of the Sylvester-Gallai theorem saying that in one SG, the points are in one-dimensional space, the question is, in which dimensional space will the points lie if they are in delta SG? If they are, fraction delta of the points are on special lines through every point. So here we see that Swastik's example tells us that, certainly the dimension can be as high as something like 1 over delta or 2 over delta, right? Because we can take 10 generic lines. And the question is, what is the right answer? How complex in terms of dimension can the configuration be? How high can be? Maybe can be as high as we want. And the main theorem, is that if P is a delta Sylvester-Gallai configuration, then the dimension, by which I mean the affine dimension of the span by the points, is at most 1 over delta squared. So it doesn't matter how many points you have as long as it's a finite number. They have to lie intrinsically in a low dimensional space. Okay, so I want to show you the proof of this. It's all simple, but it just combines somehow various ideas from various areas, combinatorial ideas, some algebraic ideas, and some analytic ideas. So I want to tell you the ingredients and of this. So is the statement clear? Everybody is happy with the statement of the theorem? Okay, so how can we prove something like this? How can we prove that the dimension of a set of points is small? So let's just take this point. There are n points. They certainly are. You can think that they're in n dimensions, right? So let's just write their coordinates. So here are the points. So this is P. So here is P1, P2. And let's just write their coordinates. So they sit in Rn. Okay. Okay, so we want to prove, what do we want to prove? We want to prove, so as a matrix, we want to prove this is the same, the rank of this matrix we want to prove is really small. And the way we are going to prove that this rank is small is by proving that the rank of some other matrix is large. So where is this other matrix coming from? What are the special lines? Special lines are just relations between the points, right? So if we have 3 points on a line, that means that there is some linear combination of these 3 points that is 0, right? So we can write these relations. Let's start writing these relations. Let's build a matrix M prime, okay? And we can look at all relations between points. So let's say P1, P2, and P3. Let's say let's say that they are triple on a line. Then we write here the combinations alpha 1, alpha 2, and alpha 3, and lots of zeros here, in such a way that when we multiply this by this, we get here 0, 0. Okay. So every row here is this basically corresponds to some special line. So this is for line of P1, P2, which happens to include, say, P3. May include other points, and then we write for each one of them, we write the relations. Okay, so we generate, let me write down all relations that correspond to special lines, and this will be the matrix M prime. I claim that it's sufficient, so to do this, it's sufficient to prove that the rank of M prime is at least n minus. Right? Everybody's happy because their product is a 0 matrix. So it's orthogonal to. So if this is high, this high rank, this cannot be. The sum has to be at most n. Okay, so that's what we are going to do. The way we are going to do this is actually, we look at somewhat smaller matrix. So we just keep certain of the rows, so we don't take every row from here. We just take some of the rows, and I'll tell you roughly which rows we take in order to do that. So M is just a submatrix. Of M prime. So just subset of the rows. And this subset will have the property that, there'll be some special combinatorial structure to the zero non-zero pattern of the entries of M. There's already a non-trivial combinatorial structure here. What do we know already about the matrix M prime? We know two things. First of all, how many ones do we have in every, non-zeros do we have at every row? Nobody's just three. Yeah. So if we look at every guy, there are maybe three. Yeah, there are three non-zeros, and the rest are zeros. So in every row, there are more. So let me write it like this. So I'll start using more general parameters. So if we look at the non-zeros in every row, let's say that at most Q non-zeros in a row, and in our case Q will be 3. Okay, but I'll prove a general theorem with some parameters. Another property that you see here is that, remember that we have to use somewhere this delta function. So we have, for every point, we have delta fraction of the other points on special lines through this point, right? So for every point, we have delta fraction, delta n rows in this matrix, right? So if we look now, we count the non-zeros here in a column, right? If we count non-zeros in a column, we want to say that there are at least k non-zeros in a column, and this k would be at least delta n. Okay. These properties are also true about M prime. Okay. But the third property that we want, and this is not necessarily a property of this matrix, certainly not property of this matrix if we take Swastik's example of having lines with many points on them, is that if we look now at every two columns, and this would be only at M, so there are some, k here, and k non-zeros here. If we look how many places do they have common non-zeros, okay? So the intersection of every two lines, so there will be at most t non-zeros intersecting in two columns, in any two columns. Okay. Now this is not necessarily true here because if we have a line with many points, then there will be many pairs on this line that will will be in the intersection. On the other hand, if every line contains exactly 3 points, it will already be fine. So here's the first claim. Maybe I should write a little here more than most people. So let me use this. So I'm going to sparsify M prime to get M, which will have all 3 properties. So I didn't say, but we will make sure that in our case T will be at most 6. So the first claim is that there exists some matrix M. I don't know how to write it. By this I mean just a submatrix, which is a KQT design. And by design, I mean just satisfies these three properties. Okay. Okay. So let me leave this the proof of this. It's a simple combinatorial, or let me say a word about it. So again, if every special line contains exactly 3 points, then there are exactly in the intersection there can be at most 3 pairs. In fact, it can be 1, but at most 3 pairs. But if a line contains many points, then we are not going to take all triples. All triples will appear in M prime. But we will not contain M, so if it contains, let's say, R points, there are roughly R cubed triples. What we'll take is only R squared triples, and you can think of it either as taking them at random, and so you don't expect pairs to appear too often. And actually, there are very simple deterministic choices of about R squared. It's sort of a design, if you know what designs are, that will have this property. So it's a simple combinatorial lemma that guarantees that that we can select a subset M, so that we don't lose on the first 2 properties. Certainly, we don't lose on the first. We will not lose on the second, and there will be at most 6 points intersecting. Okay, so now we have the situation that we have a matrix M, which is a QKT design. And what we are claiming is that every such matrix, doesn't matter what the non-zero entries are, the rank is high. Okay, so that's the claim. Is that if M is whatever is the number of rows, it doesn't matter really. M by N matrix, which is a KQT design, the rank of M is high. So what is high is N minus N QT over K. Okay? So this in general, for any K, Q, and T, this is true. Okay, and now you can check that because in our case Q and T is just a constant, each of them is a constant, and K is delta N, you get here N minus 1 over delta squared. Right, so this is a special case of this theorem. So far, everybody is... okay. So we just want to show that any matrix which has this pattern of non-zeros that has this sort of design structure, very few ones in a row, many ones in a column, but every 2 columns have very few non-zeros in common, has a very high rank, close to full rank. Okay. In this case, up to a constant, additive constant from having full rank. So how do we prove something like this? Remember, we have no control on the entries of the matrix. By the way, I should probably point out that this kind of questions, studying the rank of matrices just from the zero non-zero pattern, is appears in all sorts of areas, and people from game theory and statistics and various fields are interested in them, often with different structures. But just this general question of bounding the rank of a matrix where the entries are not fully specified, you typically just have zero non-zero information, is interesting. So that's another, you can think of it as another work in this direction. Okay, so the idea to how to prove this bound is to first make believe that we do know their values. So we just make believe that all the non-zeros are ones. Okay? And this is a really simple case, because there is a very simple spectral argument, which I'll show you. Bounds the rank. Okay? And then the second part is how to arrange to see that without loss of generality you are in this special case or very close to the special case. You can apply the same technique to do this. So let me do the claim 3, which is just claim 2 for 0, 1 matrix. Okay. On top of all this hard work, Doron wants to make sure that I time myself. Okay, so this is really simple because you can do the following. You can look at the matrix. So we are still with M, but M is now a 0, 1 matrix. And let me assume also for simplicity that there are exactly K1s per column. It's no loss of generality really in some senses. We know that there are at least, but I'll assume that there are exactly K1s. Okay. Well, look, let's call A to be the matrix M transpose. In this direction? No, M transpose. Okay. So it's the inner product of the columns with the columns. So this is an n by n matrix. So who can tell me what's on the diagonal? This is the matrix A. What's on the diagonal of this matrix? Okay, yeah. So we have okay. What's in the off-diagonal elements? It's just the intersections, right? So it's at most. So here we have at most T in every off-diagonal element. So. And remember, K's are large, they are constant times n. If the T's are small, they are just constants. This is a very diagonally dominant matrix, and for this, it's sort of easy to be. It looks almost like the identity matrix, right? So it should have high rank, and it does. And the argument is very simple. That doesn't move. It does? Yeah. Has to be strong. Okay. So how do you prove it? It's a one-line calculation. Let's compute. I will not do it all the way to the end, but let's compute the trace of A squared. What's the trace of A? Okay, and so the square is exactly n squared. Okay, on the other hand, you know that the trace is the sum of the eigenvalues, so it's the sum, so suppose that the eigenvalues here are lambda 1 up to lambda n. It's a symmetric matrix. It's the sum lambda I squared. Okay? And now you want to use Cauchy-Schwarz, as you have to in every proof somehow. And the key is, well, the rank has to come in somewhere. So the rank, some of these guys are 0. We have only just R, so let's call R the rank. So let's call R the rank of A, which is certainly at most the rank of M. Right? A is M transpose M, so So if we prove a lower bound on R, we are fine. So this goes I from 1 to R only. And now we can apply Cauchy-Schwarz, and that's at most R times the sum of the lambda I squared. Right? Okay, but what's the sum of the lambda I squared? This is this is basically the Frobenius norm of the matrix, right? Which is sum of lambda I squared, so it's R times the sum of Aij squared. So Aij, these are the entries of A. Aij squared. Okay, so you can check it if you don't know this. And so the sum of squares, well, we know what's the sum of squares of the diagonals. So we have the R. Here we have n times k squared. And so that's most. N times k squared, that's for the diagonal. It's most n squared t squared for the off-diagonal ones. Okay. And so you see what happens. If n was n minus something, n minus some,